Okay, here we go. Advent of Code Day 7. All right, so today, and we have Day 8 dropping in like less than 15 minutes. So today for Day 7, we're going to try something different. So instead of me going in cold when the stream starts today, instead I've solved it ahead of time. And then I'm just going to kind of walk through. We're going to redo it all without looking at my solution. We're going to redo the whole thing. But just kind of just talk through it because I like this one. This is interesting. This is when it starts to become a little bit more complicated, and then you can apply some of those more sort of foundational computer science data structures. Okay, so let's read through the problem. So Day 7, handy haversacks. You land at the regional airport in time for your next flight. In fact, it looks like you'll even have time to grab some food. All flights are currently delayed due to an issue in luggage processing. Okay. Due to recent aviation regulations, many rules, your puzzle input, are being enforced about bags and their contents. Bags must be color-coded and must contain specific quantities of other color-coded bags. Apparently, nobody responsible for these regulations considered how long they would take to enforce. For example, consider the following rules. Light red bags contain 1 bright white bag, 2 muted yellow bags. Dark orange bags contain, etc., etc. Okay, so lots of rules about bags needing to have other colored bags inside of them. Great. So these rules specify the required contents for 9 bag types. In this example, every faded blue bag is empty. Every vibrant plum bag contains 11 bags, 5 faded blue and 6 dotted black, and so on. You have a shiny gold bag. Fancy. If you wanted to carry it in at least one other bag, how many different bag colors would be valid for the outermost bag? In other words, how many colors can eventually contain at least one shiny gold bag? Okay. In the above rules, the following options would be available to you, right? So based on these rules here, they're saying a bright white bag can hold a shiny gold bag, right? A muted yellow bag also has a shiny gold bag. And then farther up the chain, a dark orange bag can hold a bright white bag and muted yellow bags, either of which hold shiny gold bags, as we saw here. And then a light red bag can hold a bright white bag and a muted yellow bag, and each of them can, again, hold a shiny gold bag. So you can get it through a bag or a bag of a bag, all right? So in this example, the number of bag colors out of all of our rules here that can eventually contain at least one shiny gold bag is 4. Okay. Bags have bags have bags. It's bags all the way down. Thanks for coming on. So cool. So yeah, bags on bags on bags all the way down. Cool. So that's a lot, but after reading it and looking through it, what becomes clear is that what we're talking about here is a graph, and it's a graph that has a few properties. So first, it's directed, right? So you have, let's say our bags are the nodes on our graph. There's a direction in the edge that connects those nodes, which is which bag contains the other bag. You have an outer bag and an inner bag. The other thing is that it is weighted, right? So there is that edge between two different bags has a sort of a value, or what you call a weight, associated with it. And then the other part, which is necessary in order for this to be a solvable problem, DAGs, exactly. Is it acyclic, right? That is the A in DAG, is that there is no cycle. It's never going to loop back on itself. It sort of ends eventually. And so I actually, here we go. What do I have? I pulled up a little draw.io diagram where I take their example. So here, take these rules, translate them into what that graph would look like. And so here you can see what we mean by acyclic is that At no point does it loop in such a way that it could create some infinite loop where a plum bag needs a gold bag and a gold bag needs a plum bag, and then so you have basically in a physically impossible situation to ever meet that regulation, because no, you'd have to keep on adding bags forever. This is not Barney's magic bag. All right, so basically there's, I was looking around afterwards, and there's lots of interesting ways where you can just sort of ignore the fact that this is dealing with a graph and just kind of like write a bunch of regexes to read these series of rules, and then you'll have your answer. But that's not so fun. So what I decided to do is write a bunch of code to actually define this graph, parse those rules to build the graph, and then from there, pulling out the information that we're interested in is about just a few lines of code. So let's start to think about how we're going to do this. So the first thing that I did here is, in most cases, I'm kind of starting with the input and working backwards from that, right? I think most of the previous puzzles, the first thing I've done is like, how do we parse this input? But in this case, because I have such a clear data structure in mind for where I'm going to store this input to use it, I instead decided to start with that and just sort of write like, what does this general graph look like? And I'm sure that there's Ruby libraries out there to handle this sort of thing, but that's not any fun at all to look that up. So I decided to just sort of do this, freehand. So there's no production readiness guarantees here. This is just going to be what I kind of came up with. So the first thing that I thought about was, okay, what does basically that relationship, the edge, look like, right? So let's say we have some class, edge. This gets initialized with some stuff. And so what does that look like? Well, what is the edge really in our description here? So the edge is basically this. So we have this outer bag, right? Light red bags contain one bright white bag and two muted yellow bags. And so if we go back here, right? So light red goes to bright white and muted yellow. So our edge here is basically which nodes are involved, which is the outer node, which is the inner node, and then what's the weight of this edge, right? And so then we go in here, so we have our edge, so let's just say outer, inner, and then our weight. But in this case, it's really just to sort of use language that's a little bit more close to our specific problem that we're talking about. I'm just going to call this count. So that's outer is outer, inner is inner, count is count. Okay, and then we're just going to have readers for all these things. Okay, cool. So honestly, this could probably be a struct, but whatever. I'm just going to make it a full class. It's not really going to do anything other than just be a value store for the different parts of the edge. It doesn't really do anything on its own. Now the next part that we have is the nodes, which in this case are bags, right? So let's just say this is our bag. And what do we initialize this with? Well, I'm just going to initialize it with a name, which is, the name is really going to be the color of it. So let's just call that color. So color is color. And then, so I'm just thinking about, the next thing I was thinking about was, okay, so how do I actually want to like traverse this graph? So the question that I have is, if I have shiny gold bag, what are all the bags that could contain that bag? And so what you have is you're kind of going backwards against this sort of like direction that we're saying, right? So what I know is that in order to make my life easiest, I want to be able to go from where every node basically has all of the incoming edges and all of the outgoing edges, so that I can kind of go in either direction there. So this is going to have an array of edges, like that, and then we're going to have some method add edge, which is going to take an instance of edge, and then we're just simply going to add that, throw that into our set of edges. All right, and then from there, so the question is like, okay, so for this part, the question is, how do you find all of the outer bags here? And so how would we do that given our set of edges we have? Well, we could say outers, you know, it would be edges, select only the ones, so this is a single edge. I only want the ones where the name of the inner edge, or the inner node, sorry, is my name, or the color of the inner node is my color. And so here we can say edge dot inner equals color. All right, so, and let's just add a reader here so that that actually works. And why not for edges also? Okay. Okay. Actually, we don't need one for edges because we're defining these very specific sort of like scoping methods here. Okay, and then how would I get all of the bags that this one might contain, right? If I ever wanted to go in the opposite direction, you know, don't need it for part one, but you know, it's nice to have a little symmetry here and just say, okay, so if I wanted to get all the bags that my bag might possibly contain, and then we would just basically do the opposite thing. So get all the edges where the outer bit is me. And so I'm just using color as sort of a identifier here. I know that there's only ever going to be one bag of one color, so there's no reason for me to sort of create a separate ID there or worry about whether or not multiple bags are going to have the same color. So that's why I could do something like here where I'm in the edges definition, I'm just going to use the names of those colors. I'm not going to use the actual node. Okay, so that's that. So then the next thing that you got to think about after there is like, what is the graph itself, right? So again, if I'm thinking about my problem here, and the question that I'm going to ask is, I'm not sort of at one of the sort of edges of this graph, right? One of the, either what you might consider the beginning, the bag that is not contained by any other bag, or the end, being the bags that do not contain any other bags. But rather my question has me starting kind of in the beginning here. And so when I'm thinking about what is my graph going to do in order to make solving that question easy, the idea that I had in mind was that I'll initialize it with some input, which I'm going to assume is my directions, and I'm going to do something with that. I don't know what it is right now, so I'm just going to put that there. But if I think about what am I going to sort of store my actual data in for this thing, is I'm thinking that it's going to be a hash where the nodes are going to be keys. So right, we're going to, for example, we'll have light red, and then that will simply point to the node object, so that I have a direct line to all of the nodes in my graph, so that I can start any sort of search from any given node, rather than having to worry about you know, only storing the beginning of the graph and then having to traverse that to find it. Cool. So this just starts as empty like this, and then so there we go. So then what else does a graph do? So you want to be able to add these sort of to build this graph, right? And so the way that I'm thinking about building a graph is really building the edges. And if either of the nodes involved in the edge is missing, then I'll create that node. But really, I don't need to have a create node step, create another node step, and then link those two nodes with a relationship. I can just sort of like define those edges and then fill in the nodes wherever they're missing. So to that end, we'll have this basically this method add edge. And so what is that going to do? So let's just say that this, basically we're going to kind of call this exactly the same way that we're initializing an edge. So it's going to take an outer, inner, and then whatever that count is. So what do we have? So the first thing that we're going to do, like we said, is if that node doesn't exist, then we're going to create it. And so the way that we could do that is we could say outer bag is this graph at the key for it. Otherwise, both get it and set it to at the same time a new bag using that name as the color. Right, and then we're going to do the same exact thing. Oops. Same exact thing for inner. So here, what do we got? Here we go. I can do that. I can Vim. Okay, so outer is inner. Bum bum bum. Cool. Great. So now we have our two nodes, and now because, like we said, where we want basically each node to hold on to that edge, right? It's not simply like if you were to think about like a linked list, this would be sort of a more doubly linked list where you can go forwards and backwards. You don't just have to go in the direction of the graph. So first, let's just make that edge. So edge is edge new, and again we're doing outer, inner count, and then each of these outer bag will add an edge there, and then inner bag will get the same thing, so that each one is has a reference to that, so we can go backwards and forwards. Boom, boom. Okay, great. So now we have basically we have our graph, and we can start to think about how we're going to parse that input. So let's take another look. What does this input actually look like? So we have light red bags contain one bright white bag, two muted yellow bags, dark orange bags, right? So okay, so basically it is, we have this color and then bags, and then we have rules about how much it contains. So what I'm thinking of is I'm going to split this up into two different ways to capture. So first thing I'm going to capture is I want to capture what's the outer bag in this rule, right? So I want to get this word, whatever's before the first instance of bags. Then I'm going to grab whatever comes after contain, and I'm going to treat that as it's a list of one or more inner bags that I'm going to parse separately, because the difference there is that there's a number in front of it. And then we can use that to build these relationships. Okay, so let's see what this would look like. So basically, what are we going to call this? Let's just call this rule parser. Rule parser. Okay. And this is going to result in basically a bunch of edges. So we initialize this with some string, and then what it gets is once you, well, let's just say it's initialized with a rule. It is rule parser after all, it should parse some rules here. So then we're going to give that a rule. Reader on edges. Cool. All right, cool. So let's define this parse rule. Okay, so like we said, we're going to do two different regular expressions just for simplicity. I'm sure that there's some sort of witchcraft that I could do to basically capture n number of things plus one thing. I don't know. I don't really want to think about that. The simple thing for me is just to split it up. So we have the first set of captures is we're going to match on that first part, right? And the first part is, well, most importantly, the line starts. That's where the beginning starts. And so what I want to get here is just the name of this outer bag. And so I'm going to use something I recently learned about this feature in Regex. I had known about it, but I never really used it before, but now I kind of love it. And that is named captures instead of doing index count or numerically identified captures, which is no name. I just like the names. It makes it so regexes are kind of a little bit closer to readable, which is, it's nice. All right, so this outer number is, what's that? It's any number, it's a words, characters, or space characters occurring more than once, right? Because we can have spaces in here. But it's basically whatever that happens until you get a space and the word bags contain. And then there's another space, and then we're just going to capture everything else that comes after that. And again, we're going to name that because we're being fancy. And so this is inner is just whatever forever. And then we go like that. Okay, so that's our regex. And then we're just immediately going to pull from that. I'm just going to close this named captures to just, instead of getting a match data object, we're just immediately going to go and get that as a hash. That's what named captures is going to do there. Cool. And now from here, what are we doing? So first, let's look at the two parts we have. So outer is caps at outer. Oops. There we go. All right. And then inner is our caps at inner. Nice. All right. So now the next part that I'm going to do here is I need to parse that sort of second part of the regex that I was too lazy to do in the first part. And then what am I going to do with that? So what I'm going to do is I'm going to parse these inner rules, and then we're going to map over those. Let's see, this is going to be an edge, right? It's going to return basically part of an edge. And then what we're going to do with that is we're going to just add in the outer bit. So in this case, actually, you know what? I'm just going to do it real. Instead of merging, because I'm just thinking out loud here that when I parse those inner ones, it's probably going to be something similar to this with named captures. Where my keys are going to be strings, but I just want these keys to be symbols. So what might I do about that? So this is going to be some list. What are we going to do here? Well, let's just see what happens. Let's try it out. And then we're just going to say outer is outer. Okay, cool. Right, so because we want them to have all, so that's just going to parse our rule. That's going to result in these edges, which we can then use to build a graph. Awesome. Okay, so now let's talk about what does parse inner look like. Oh, and also, apparently, there we go. So what does parse inner look like? Parse inner takes inner rule. There we go. And really, this is, well, whatever. It could be plural, but it might not be. Okay, so how does parse inner work? So the first thing is we have one sort of special case that we can immediately jump out if we see, which is this one, no other bags. So the first thing we can say is return empty if inner equal no other bags, right? Okay. So just right away we're going to say, okay, there's nothing here if this is no other bags. Otherwise, okay, so now what we're going to do is a way to basically pull out a repeating pattern, and it's boags. To pull out a repeating regex in a string is the great little method scan. And so here, if we do something like inner scan, so what does this format look like? It's basically, it's one or more digits. All our examples here are 1 digits, but let's just assume it can be a multiple digit number. So 1 or more digits, and then it's some number of, again, words and white spaces, just like we saw before, and then the word bag, maybe the letter S, maybe a comma, and then right, because it's going to repeat again. Okay, so let's see what it would look like. So the first thing, and we want to here, we're going to capture everything and then that we want individually, and then what scan is going to return is basically those captures as an array. Okay, so let's see what that looks like. So what does it start with? It starts with 1 or more digits, right? We're going to capture that. That's the count. And then after that, we have it's A through Z or space. We can even say it's just word or space like we did earlier. And then 1 or more of those things. And then it's the word bag, maybe the letter S, right? And then we're going to say, boom, we're doing that. So then, yep. Oh, what is it complaining about? What is the matter? Syntax. Inner scan. Ah, here we go. We didn't complete this thing here. This group. Okay. I think that's it. Okay. Yeah. Great. All right. So then we have. Okay. So we're doing this, and then what we're gonna do is we want to turn this into a hash. So we say each with object do. And then, so this is an array, and we're going to kind of destructure this in our loop here. Thanks for stopping by. Cool. So what do we got? We have the count is the first match, right? We have color is the second match. After that, we have the hash. Sorry, I forgot to do each with object. Cool. Okay, so then we got that. So let's say, what are we going to save this as? We're going to save this as, oh, actually, so you know what? Let's not do this. Let's do map. Okay. Let's map that into, because we need that above. So we could say inner is whatever the color is, and then count is the count. Cool. So then that way up here we got to merge, right? That's how we have to do that. Okay. Okay. Sweet. Okay. So I think, there we go. So now we have that. Okay, so now, so we have a way to parse the rule into something that we can use in order to call this add edge function in order to build our graph. And so now the last thing that I have to do is what I'm going to do here is actually define this relationship, or how you would do that. So let's say we're going to say that the way that you get a graph is you call this method build and you pass it that input, right? So let's get rid of this. Let's just say that initialize does nothing. Then what we're going to do is we're going to start a new graph, and then we're going to tap into that graph. And then we're going to basically go through this input and then use that input to add edges. So how can we do that? So the first thing that we could do is we could say edge, maybe edge definitions is, we'll start a new rule parser on the input, right? So what we would want to do, input split n, each do rule. Then we would call a rule parser on that, right, to get those edge definitions. Except, what is it called? It's edges, right? But do we actually need to, what do we need to do here? We don't actually need to do that. So we can just immediately use those, right? So, because what we want to do is edges, each do edge, right? And then what are we doing here? So we're going to call this add edge. And this is going to be graph add edge. And then it's edge outer, edge inner, edge color, right? Oh, no. Count. I think that's what it should be. Oops. What did I do? Yeah. Inner, outer, inner count. Okay, great. So I think that's all that I need to do here. Yeah, so basically just going through all of our input, splitting that into new lines, treating each new line as a rule to be parsed by our rule parser. That's going to result in a bunch of edges. And then we will use those, add those to the graph. Okay. We don't need those if they're going to be empty. Cool. Okay. This is looking pretty good. Okay, so let's see what's going on here. So let's write some tests. So live spec. Okay. And so what do those tests look like? So the first thing we do here is this is going to be our input if we're starting this, right? So let's see. So first thing, let's get that file in here. Day 7 live. Okay. RSpec, describe, what is this? Graph, do, let, rules, do, lines. Actually, this is like this, lines. Okay, awesome. Lines, great. So that's just going to be what we just copied out of the internet. The internet. Okay. Now we're going to do the most fun thing in the world, which is indent these things. Okay, great. All right, so those are our rules. So let's look again. What does how are we going to call this basically? So we're going to describe, so build is going to build, except what do we actually want to do here? We want to know from any given point what is the number of bags that could be a containing bag, right? That's the first one. And so if we look here at our graph and how things are sort of defined here, we're counting all of the outers. And so let's say count outers for some color, right? So whatever color that is. And then so how do we do that? So we say the bag that we start with is whatever graph at color, right? So we just grab that. And then, so what's going to happen here? So first thing is that there might be no containing bags, right? So if we're at one of our starting, like light red, no other color contains light red. So that's going to be our base case here because we are going to be using recursion. Cool. So the first thing in recursion, handle your base case. So basically, return. Let's see. What are we going to do here? I'm struggling thinking about this as a problem of counting. So what I'm going to do here instead is just have something that basically returns a list, and then you can do whatever you want with that. You can count it whatever you want. So my base case is going to be returning an empty list if bag.outers is empty. Okay. Now, what's my sort of, I forget what you call it, recursion case? That is bag that we're currently at. So the ones that are immediately outside of this one, and we're going to map on, what do we have? Yeah, so I really just want to grab the name of it, right? So outers is going to return me the edges. And really I just, for this, I don't want the edge, I just want the name of the color. And so here I'm going to map like that. Okay. And so that plus, and this is where we start to recurse. So this, so basically we want to, so first thing I'm going to do is outer names, right? Just going to say this because I'm realizing that I'm going to have to do this twice. So bag, outers, map, outer. Okay, so that's outer names. And what I'm returning is outer names plus outer names dot map, right? Because this is taking a name, and that's what we need to recurse with. And so we can just say n, and then that is all outers for n. Okay. Cool. And so great. Okay. So this should basically, at the end of the day, this is going to return us a list of all the colors that could contain this color. And so let's use that in our test. So just let's say it can count all containing bags. Do and so we have, how do we actually make this graph here? Well, we can initial build it, right? So we can say graph is graph.build. What do we call this up here? We call this something. Rules. Okay. So build a graph given these rules. And then what are we going to do? So we want to know graph all outers for, I believe it's shiny gold. Shiny gold. And then, so if it's all out, so there's a few repeating. So if we go back to our grid here, right? So bright white, if I get the parents for shiny gold, bright white, muted yellow, they both have dark orange and light red as parents. So that's going to show up multiple times. And so I'm just going to do unique count, right? Because all outers might have multiple. And there's ways that you can resolve that. I think like if I used a set instead of an array, then that would fix that problem. But calling it's not going to be a very long list, so I'm not like super worried about calling unique. And another thing I'm just thinking here is that this should be a flat map, right? Because this is going, each of these is going to reproduce an array, but I just want to add this all together into one flat list that I'm building up as I recurse. Cool. Okay. So that's that. So let's see. I believe I'm supposed to expect this to equal 4. If I look back at my instructions, 4. Okay. Let's see. What do we got here? Ruby, RSpec, day 7 live spec. Okay, great. That's working. Cool. So my puzzle answer was 326 that I got with my other solution, which is very similar to this one, but not totally the same. We are doing a bit here. So let's say day 7 live solution.rb. And then, so let's look at another. Okay. Great. I don't need to make a live version of the input. That's the same. Okay, so graph is a graph that we build with the input. And then, so what was the question here? How many bag colors could eventually contain at least one shiny gold bag? So the same as our test. So we can even just look. So it's graph all outers for shiny gold unique count. Okay, part 1. And then we can say down here, puts part 1. So let's see if we got this right. Ruby solution or day 7. Okay, 326. Oh, oops, I did the live. That's the other one that I did. I want the live solution. 326. Cool, so it matches. Okay, awesome. Cool, so again, there's a lot of quicker ways to do it than that. But that one has the really fun benefit of letting you kind of build up the whole graph. And now, like, you could answer all sorts of questions about this, you know, that regardless of what this one is. For example, part 2. Okay, so again, they're talking now about going in the opposite direction, right? So it says, consider again your shiny gold bag and the rules from the above example. Faded blue bags contain 0 other bags. Dotted black bags contain 0 other bags. Vibrant plum bags contain 11 other bags, right? They get 5 faded blue and 6 dotted black. Dark olive bags contain 7 other bags, 3 faded blue and 4 dotted black. Right, so a single shiny gold bag must contain a dark olive bag and the 7 other bags that dark olive bag contains, plus 2 vibrant plum bags and the 11 bags with each of those. So a total of 32, excuse me, 32 bags. I don't know who has that many bags outside alone of inside of one another, but bags on bags on bags. So of course, the actual rules have a small chance of going several levels deeper than this example. So be sure to count all the bags, even if nesting becomes impractical. Topologically. And that they mean real world-ish. Okay. So here's more examples, right? And then they say here that a single shiny gold bag must contain 126 other bags. So this feels like another test case. So let's go in here and get it done. So let's say let's just call this rules number 2. And so once again here, lines, lines, boom, okay. Cool. So these are new lines, and then it can count the number of bags contained, let's say, for this one. Right, so it's sort of in some ways, it's not the exact opposite of that one, because in this one we just completely ignored the weights on the edges, and we just cared about the number of nodes connected. But now we care about, it's basically nodes times their weight. Right, so this one says, right, a single shiny gold bag must contain 126 other bags. Okay, so how would we define this one? So it's going to be very, very, very similar to all outers, right? Because we're doing the same sort of thing. We're recursing along the paths of this graph. In this case, we're just going in the opposite direction. Before we were going back up to the containing bags. Now we're going down through all the bags contained. And there's another key important difference here, which is that we're taking the weights into account, and we're summing up all of those basically child bag times their weight. All right, so let's say product of children or something for a color. Okay, and then so first thing we do again is we have bag is whatever the graph node is for that color. All right, and then so here, once again, recursion, so we need our base case. So what is the base case? So the base case is that the bag contains no other bags, in which case, what is the number of bags that we have is simply 1, the bag itself. So we could say return 1 if bag dot, so we define this as inners. Okay, so bum, bum, bum. Cool. So return 1 if bag dot inners is empty. Okay. Great. So we have our base case. So then what is the rest of the cases? So the rest of the time we're going to return 1, which is the bag itself, plus the bag's children. So bag inner dot count, all the bags that it contains. Except, sorry, we're not going to count those. We're going to add those up by, let's just call that I. So by its weight, so that's count times the number of its own children, right? So this is where we recurse, because it's not only that you have 3 lavender bags, you have 3 times the number of bags that a lavender bag contains, right? And so that's why we say here it's the weight of that edge, or in other words, the count here, times product of children for that specific color. Right? Yeah, that's what we want. Because inner here is edges. Okay. Cool. So, well, let's see if we're actually right. So now if we go back to our test. So once again, we'll say graph is, we want to build a graph from this input of rows 2. And then we say expect graph product of children of shiny gold. And then here's a key part, which I realized. So if we go back and look at this, so basically every bag that we're counting is going to count 1 for itself. Now they're asking the question about the first bag, which is the yellow bag. So it turns out, so for example, the shiny gold bag must contain 126 other bags. So our algorithm or method, whatever you call it, that we wrote here, product of children, is going to return the total number of bags that we have if we start with a shiny gold bag, including that shiny gold bag. So in order to get the number that we need here for this test, what we're going to do is we're going to subtract 1 from the results of our method, and then that should equal the correct number, which is 126. And so let's do that. Let's see, inner. Okay, yeah, I thought that looked weird. Okay, so we have it here. It should be inners, right? Because that's a list of them, not just 1. So let's do this again. Ooh, string can't be coerced into integer. Fun, fun, fun. So something's happened in our sum function that is not, that we don't like. So what's happening here? So we're summing on you know what? No. That does look a little weird though. Inner.inner. Thought it would help to change it from I, but it doesn't really help. So what is happening here? 1 plus so what is happening? Let's see once again what's going on. Okay, so string can't be coerced into an integer. Interesting. So it seems to be around this product of children method. Let's take a look at what that is. All right, let's have some fun debugging. So what is happening here? String can't be coerced into integer. How can I, let's see. Corner, cry. Am I trying? Oh, I know what it is. I know what it is. I'm just thinking, what is going on here is that I'm trying to use count as a number, and I don't think that I ever made count a number when I pulled it out of this thing here. Yeah, when I use scan. That is the problem, I believe. Boom. Okay, nice. That was the issue. Cool. So there we go. And then if we want to doubly confirm that we got this, part 2, graph product of children for shiny gold, -1. Let's see what this is. So if we do Ruby day 7 solution, which I already put in, I know is right. Nice. Day 7 live solution. Same numbers. Woo! Okay. So that was quite a bit of fun. So if you're looking around out there, you're going to see a lot of solutions that are shorter and far less code. But those solutions don't define these these graph objects, which are a lot of fun to play around with. And there's a lot of cool visualizations out there you should check out that use to great advantage of the fact that that is a graph. Cool. So day 8 is out, I think, right? Yeah, day 8's out. I'm not going to do that right now because it's 12:40 a.m. and I have work tomorrow. So we'll save that for tomorrow. Have a good night.